Welcome everyone. In this video, I will be covering 11.9, chapter 11, section 9, representation of functions as power series. In this section, we will learn how to represent certain types of functions as sum of power series. This strategy is useful for integrating functions that don't have elementary antiderivatives, for solving differential equations, and for approximating functions by polynomials. We'll start off with our familiar series, which is a geometric series. We start with an equation that we have seen before, equation 1 over 1 minus x, which is 1 plus x square and so on. So if you consider a geometric series, infinite geometric series, like this 1 plus x square, etc., with common ratio less than 1, then the sum of the series is a divided by 1 minus common ratio. A is 1, 1 minus common ratio is x. So we can write the function 1 over 1 minus x. In this way, 1 plus x square and so on in the expanded way, when absolute x is less than 1. So 1 over 1 minus x is written as 1 plus x square, x cube, etc. in the expanded form. In the sigma form, it can be written as sigma x to the n, x to the exponent n runs from 0 through infinity, whenever absolute x is less than 1. The series here is an infinite geometric series, as we all know, with starting term a equal to 1 and common ratio equal to x. We are now expressing the function f of x equal to 1 minus x as a sum of power series. One important thing, this will be quite often used throughout the section, this idea. One thing you can remember is that, so if you have 1 minus 1 over 1 minus x, you write that as 1 plus x square, etc. And in the sigma form, it is x to the power n, common ratio to the power n. So whatever be x, so if I replace this x by some box, let's say, then you can consider this as 1 plus the box, then the box square, the box cube in the expanded form, which is equal to sigma, whatever goes inside the box, to the power n. So remember this, the reason why I'm saying this is that, so whatever be x, in this box you can have x square. In this box you can have a negative x. So all you need to do is to write this as sigma n varying from 0 through infinity. Here also it is 0 through infinity, box to the power n. Whatever that goes inside the box goes here, box to the exponent n in the sigma version. The geometric series of equation 1 is shown in this figure. So we know that a series is a limit of the partial sum, right? Limit of the partial sum. So if I consider Sn(x), Sn(x) is the sum of n terms of this geometric series. So Sn(x), S sub nx, partial sum, is first sum of n terms of the series. So it's 1 plus x square, etc. up to x to the power n. The limit of this is equal to the sum, which is 1 over 1 minus x. So if you take, let's say, two terms, 1 plus x, if you consider only two terms, it's S2. So S2 is shown here, it's a linear one. And then S3 is a parabolic one, 1 plus x square. So as you increase the number of terms, in the partial sum, as you take more and more of the terms, it will resemble this function 1 over 1 minus x in the long run, right? So that is what the figure shows. So it can be approximated by these polynomials. Notice that as n increases, Snx becomes a better approximation to f of x in the interval -1 to +1, because we know that absolute x is less than 1. So in that interval, it becomes the best approximation, a better approximation to the function f of x. Let's try this example based on this. Express 1 over 1 plus x squared as a sum of a power series and find the interval of convergence. So notice that in this section is all about representing certain functions as sum of power series. So we are going to represent this 1 over 1 plus x squared as a sum of power series. And in the last section, we understood what we know what we mean by interval of convergence. That means for what values of x, or in what interval of x will this function be convergent. So let's take this 1 over 1 plus x squared. Before that, just rewrite what we learned now. 1 over 1 minus x is 1 plus x squared, etc., which in short can be written as in the sigma notation, it can be written as sigma x to the power n. So recognize that. Now we will write 1 over 1 plus x squared as 1 over 1 minus, we want to write everything this way, 1 over 1 minus a box. Right? So we want to write this as 1 minus of minus x squared. So what goes inside the box? Negative x squared. So it is equal to 1 minus x squared plus minus x squared the whole square minus x squared the whole cube, etc. Then written in sigma notation, it will be, so as we said earlier, it is box to the power n. Here the box is negative x squared, that is negative x squared to the power n. So it can be written as 1 minus x squared plus x to the power 4 minus x to the power 6, etc. And this can be written as a sum sigma n varying from 0 through infinity, negative 1 to the power n. Negative x squared is negative 1 times x squared. So it is negative 1 to the power n, x squared to the power n, that is x to the power 2n. So you can write like this whenever absolute x is less than 1. Here you can write like this when it converges when absolute negative x squared is less than 1. You can write like this power series only when the common ratio of this one is less than 1, which means absolute x squared is less than 1, which implies that absolute x is less than 1. So therefore, the interval of convergence, so this series can be written like this only when absolute x is less than 1. So the geometric series converges when absolute negative x squared is less than 1 or when absolute x is less than 1. So what is the interval of convergence? Interval of convergence is where which interval the series converges, which is negative 1 to positive 1. In this problem, you don't have to verify whether the series converges at the endpoints or not. As long as long as the series is comparable to a geometric series, or it came from a geometric series, it got derived from a geometric series, you know very well that um, only when the common ratio is the absolute value of the common ratio is less than 1 will it be convergent. Whenever it is equal to 1 or more than 1, it's going to be divergent. So we are not required to verify the endpoints scenario in this particular case. Let's try the next example. Example 2. Find the power series representation for 1 over x plus 2. Always the goal is to write the series as 1 minus of something like that, so that we can write everything as a geometric series that we discussed earlier. So we want to take this expression, the given function, 1 over x plus 2, and you want to make it look like the geometric. So take the 2 out, then it will become 1 plus x over 2. So now this looks like 1 over 2 times 1 over 1 plus x minus x over 2. Or it is 1 over 2 times 1 over 1 minus of minus x over 2. This is kind of box. So now we can write this as, by using the same principle that we wrote. If it is like this can be written as 1 plus box square, etc. In sigma notation, it can be written as box to the power n. The same idea. So 1/2. Then you can write this as sigma. What goes inside the box? In this case, it's negative 2 to the power n varying from 0 through infinity. That is 1/2 sigma negative 1 to the power n, then 2 to the power n times x to the power n. Then we can, in order to combine all the 2's together, the 2 can be brought inside the sigma. 2 to the power n times 2, just 2 to the power n plus 1. So if we expand and write, so we can give values successively for n equal to 0, n equal to 1, and so on. When you give successive values here, you're going to get n equal to 0 is going to be x to the power 0 over 2 to the power 1. So it's going to be 1 over 2, 1 over 2. Then n equal to 1, which will be negative. Negative x to the power 1 divided by 2 square plus negative 1, then n equal to 2. That will be positive. So x square divided by 2 cube, etc. The terms are going to be alternatively positive and negative. So where does this series converge? As it is geometric series, so as the series that we have got is a geometric series, so it converges when the common ratio is less than 1. What is the common ratio? Negative x half, because this part is a geometric series part. So common ratio is negative x over 2. This absolute negative x over 2 should be less than 1. Or in other words, absolute x should be less than 2. So what is the interval of convergence? The interval of convergence for this problem is negative 2 to 2. You don't have to worry about checking the endpoints because the series is comparable to geometric series. So this is part A of this concept video for section 11.9. We will continue this material, the concept, in part B for 11.9.